Picture a simple drawing of the solar system. At the center is the sun. Around it, Earth follows a thin oval line, returning to almost the same place after 1 year. It is one of the first astronomical pictures many of us learn, and for most everyday purposes, it is a very good one. Tonight, though, we are going to look at that familiar orbit from farther and farther away. We will begin beside the sun, where Earth's path looks almost closed. Then we will move outward to the scale of the Milky Way, where the sun itself is traveling. And eventually, we will ask what Earth's motion looks like against one of the largest reference frames. Astronomers can measure. You do not need to keep track of every speed or angle along the way. The important idea is simpler. A path depends on where you are watching from. From the point of view of the sun, Earth moves around it at roughly 30 kilometers each second. Over the course of 1 year, that motion carries our planet through a complete orbit. But during that same year, the sun has not remained where it began. The entire solar system is traveling around the center of the Milky Way at roughly 230 kilometers per second. So while Earth completes 1 familiar year, the solar system travels on the order of 7 billion kilometers along its much larger galactic journey. That does not make the textbook picture wrong. It only tells us what the picture has chosen to leave out. When an astronomer studies the motion of a planet, a spacecraft, or a star, the first useful question is not simply, how fast is it moving? The first question is, moving relative to what? That phrase, reference frame, can sound more abstract than it really is. A reference frame is simply the set of coordinates from which we describe position and motion. We choose an origin, decide which directions count as fixed, and then measure everything else from there. For many solar system problems, the sun provides an excellent origin. For a spacecraft approaching Mars, engineers may instead use coordinates centered on Mars. For a spacecraft traveling between planets, a barycentric frame can be more convenient. For galactic astronomy, the center and plane of the Milky Way become useful. And for cosmology, astronomers can define a frame using the cosmic microwave background. None of these coordinate systems is secretly more real than the others. They are tools. A good reference frame removes motion that is irrelevant to the problem and makes the motion we care about easier to see. Suppose we want to describe Earth relative to the sun. That is a natural choice. The sun dominates the solar system's mass, and Earth remains gravitationally bound to it. In this frame, Earth's motion is close to the clean ellipse drawn in textbooks. This view is useful enough that it can guide extremely precise calculations. A spacecraft traveling from Earth to Mars does not need its navigation display to show the solar system sweeping around the Milky Way at the same time. Earth, Mars, the spacecraft, and the sun all share most of that larger galactic motion. For the problem at hand, much of it can simply be left outside the frame. But now imagine that our viewpoint moves far beyond the solar system. Instead of fixing the sun near the center of our map, we fix our coordinates to the Milky Way. The solar system is no longer stationary. The sun is traveling around the galaxy, carrying Earth with it, and immediately Earth's familiar closed orbit changes shape. It cannot return to exactly the same galactic location after 1 year because, while Earth has been traveling around the sun itself has moved billions of kilometers farther along its galactic path. The little ellipse has been carried somewhere new. This is the grain of truth behind many dramatic animations of the solar system moving through space. Earth really does trace a different path when we stop using the sun as our stationary reference. But the details matter. A common animation places the planetary orbits almost like a wheel facing directly into the solar system's direction of travel, with the planets trailing behind the sun in a long corkscrew. The real solar system is arranged differently. Earth's orbital plane, the ecliptic, is tilted by roughly 60 degrees relative to the plane of the Milky Way. That means Earth does not simply remain behind the Sun, as both move through the galaxy. During different parts of the year, Earth's orbital velocity points partly with the Sun's larger galactic motion, partly against it, and partly across it. Seen from a galactic frame, the result is not a neat tail. It is a small, repeating three-dimensional variation laid over the Sun's enormous journey around the Milky Way. Even this picture needs one more caution. The Sun's orbit around the galaxy is often sketched as a smooth circle, because that is the easiest way to show the scale. The real galactic orbit is more complicated. The Milky Way is not a point mass with the Sun circling it like a planet around a star. Its mass is spread through a disk, a central bulge, a halo, and many smaller structures. The Sun, therefore, follows an orbit shaped by that distributed gravitational field. For our purposes, however, the simple picture is still useful. The solar system is moving around the galactic center, and Earth is making its annual orbit while that larger motion continues. The scale difference is almost absurdly large. Earth travels around the Sun once per year. The Sun needs roughly 230 million years to travel once around the galaxy. One human lifetime, therefore, covers only a minute fraction of one galactic orbit. Yet, both motions are happening at the same time. The familiar ellipse has not disappeared. We have simply placed it inside a much larger journey. And before we move farther out, there is one more correction to make. Even the Sun does not follow a perfectly smooth line. The center we have been treating as stable is itself moving slightly. To understand why, we have to look not at the edge of the solar system, but back toward its invisible center of mass. The center of the solar system is not quite the center of the Sun. Instead, the Sun and every planet move around a shared center of mass called the barycenter. Because the Sun contains almost all of the solar system's mass, that point usually lies close to it. But close is not the same as fixed. Jupiter matters most. It is more than 300 times as massive as Earth, and its gravity is strong enough to shift the solar system's center of mass away from the Sun's own center. Saturn and the other planets add smaller changes of their own. As the planets move through their orbits, the barycenter moves as well. Sometimes it lies deep inside the Sun. At other times, the arrangement of the giant planets can place it beyond the Sun's visible surface. A useful way to see this is to imagine the Sun and Jupiter by themselves. Jupiter takes almost 12 years to go around the Sun, and the Sun responds by moving around the shared Sun-Jupiter center of mass. Add Saturn, Uranus, Neptune, Earth, and the other bodies, and the location of the full solar system barycenter becomes a continuously changing result of all those positions. So the Sun is not simply waiting at the middle, while everything else circles around it. It moves too. The motion is small compared with the scale of the solar system, and almost invisible compared with the Sun's journey around the Milky Way. But it is real. If we could watch the solar system's center of mass from far away, the Sun would make a slow, irregular motion around that changing point, while the planets followed their own much larger paths. This adds another layer to Earth's trajectory. Relative to the Sun, Earth still follows its familiar orbit. Relative to the solar system barycenter, the description becomes slightly different, because the Sun itself is moving around that shared center, and relative to the galaxy, both of those motions are carried forward together. There is no need to picture this as a tangle. The important thing is that each new reference frame adds motion that the previous frame was allowed to ignore. Astronomers use the same principle when they study distant stars. A planet cannot shine brightly enough to reveal itself in every telescope, but its gravity can still move the star it orbits. As a planet travels around a distant star, the star responds to the planet's pull by making a much smaller motion of its own around their shared center of mass. For a large planet close to its star, that stellar motion can sometimes be measured. One method looks for tiny changes in the star's velocity toward and away from us. Those changes slightly shift the wavelengths of the star's light. Another method attempts to measure the star's position itself, searching for a very small movement across the sky. These methods are related, but they are not the same. Radial velocity observations detect the back and forth component of stellar motion along our line of sight. Astrometry tries to measure the star's tiny change of position across the sky. Each is a different projection of the same gravitational response. In both cases, the planet may remain unseen. Its presence is inferred from motion. So the slight movement of our own sun is not just an inconvenient correction to a textbook diagram. It belongs to the same gravitational logic that allows astronomers to discover worlds around other stars. And this is where the idea of a perfectly smooth solar system begins to fade. There is no single rigid machine carrying Earth through space. The planets pull on the sun pulls on the planets, the giant planets pull on one another. Earth's orbit changes slightly under these combined influences, even though its overall motion remains remarkably stable across human timescales. If we watched for only 1 year, the familiar ellipse would serve us very well. If we watched for centuries, smaller variations would begin to matter. And if we extended the view across tens of thousands of years, even the orientation and shape of Earth's orbit would no longer remain exactly the same. Earth's path changes slowly. Its orbit becomes a little more circular, then a little more elongated. The tilt of Earth's rotation axis changes by a few degrees over long periods. And the direction of that axis slowly turns, tracing a broad circle against the distant stars. These are among the motions grouped under the name Milankovitch cycles. The change in orbital eccentricity operates mainly on timescales around 100,000 years. The variation in axial tilt has a cycle of roughly 41,000 years, and Earth's rotational axis completes its slow precessional motion in about 26,000 years. The climate effect associated with precession is a little more complicated than that single axial period, because the orientation of Earth's orbit changes too. In paleoclimate records, a strong precessional rhythm often appears near 23,000 years. None of these changes is dramatic from one human lifetime to the next. The seasons still return. The constellations still seem almost fixed. Earth still completes its orbit each year. But on geological timescales, these slow changes alter how sunlight is distributed between seasons and latitudes. For climate, the important point is not usually a large change in the total amount of sunlight reaching the planet over an entire year. It is the redistribution of that sunlight. A different axial tilt changes the contrast between seasons. A different orbital shape changes how Earth moves through different parts of its orbit. Precession changes where the seasons fall relative to Earth's position around the Sun. Those orbital patterns can be traced in natural archives. Layers of ocean sediment preserve changes in microscopic organisms, and dust. Ice cores preserve information about ancient atmospheres and temperature. Together with other records, they reveal long climate rhythms that can be compared with calculated variations in Earth's orbit. The match is not a story of orbital geometry acting alone. Ice sheets reflect sunlight. Greenhouse gases affect how heat moves through the atmosphere. Ocean circulation changes. Land surfaces and ecosystems respond. The orbital cycles change the distribution of solar energy, and the climate system amplifies and reshapes that, forcing through feedbacks. Together, these processes help pace the long alternation between glacial and warmer periods. The orbit we usually draw as a permanent ellipse is therefore better understood as a useful snapshot. It is stable enough for navigation, stable enough for calendars, stable enough for everyday astronomy. But it is not frozen. And once we accept that Earth's path can change even within the solar system dust, we are ready to widen the frame again. Because the sun's own path through the Milky Way is not perfectly flat either. The Milky Way is often pictured as a thin, luminous disk. Most of its visible stars, gas, and dust are concentrated within that broad, flattened structure, while the Sun travels through a quieter region, well away from the galactic center. From above the galaxy, the solar system would appear to move around the center in a vast orbit. But seen from the side, another motion becomes visible. The Sun does not remain exactly in the middle of the galactic disk. It moves above and below it. The reason is gravity. Because so much of the galaxy's ordinary matter is concentrated toward the disk, a star that moves above the midplane feels a gravitational pull back toward that denser region. As the Sun approaches the midplane, it gains vertical speed. It passes through. Then it continues to the other side, gradually slowing as galactic gravity pulls it back again. The motion resembles an oscillation. If the Sun's long orbit around the Milky Way could somehow be unrolled into a straight path, its vertical movement would look roughly like a slow wave drawn along that line. The timescale is enormous. Models generally place a complete up and down cycle on the order of several tens of millions of years, with estimates around 60 or 70 million years often used as a useful approximation. That number should not be treated like the length of an Earth year. The Milky Way is not a perfectly smooth gravitational system. Its disk contains spiral structure, gas clouds, stars, and other concentrations of matter. Our measurements of the galaxy continue to improve, and the exact details of the Sun's vertical motion depend on how that galactic mass is modeled. Modern stellar surveys have also shown that the galactic disk is not a perfectly settled sheet. Large groups of stars can carry vertical motions and wave-like structures of their own. So when we speak about the Sun oscillating through the midplane, we are using a useful dynamical picture rather than describing motion through a rigid, perfectly flat surface. Still, the broad picture is secure. The solar system circles the galaxy while also moving through its disk. Once again, a path that looked simple from one viewpoint becomes richer when another dimension is added. This movement has occasionally inspired more dramatic ideas. Far beyond the planets lies the region associated with the Oort cloud, a distant population of icy bodies thought to extend far around the solar system. The Oort cloud has not been photographed as a complete structure. Its existence is inferred from the orbits of long-period comets, and from models of how small icy bodies could have been scattered outward early in solar system history. At such great distances, the Sun's hold is comparatively weak. The gravitational field of the galaxy can, therefore, matter over very long periods. Galactic tides can alter the orbits of distant objects and may help send some of them inward toward the planetary region. Passing stars can disturb those distant orbits too. The outer solar system is not completely isolated from the stellar environment around it. From those real physical effects came a more speculative question. Could repeated passages through different parts of the galactic disk increase the number of comets reaching the inner solar system? And if so, could that create a repeating pattern in Earth's geological history? Scientists have explored versions of this idea for decades, but no convincing periodic connection between the Sun's motion through the galactic plane and mass extinctions on Earth has been established. The distinction is important. Galactic gravity can influence distant comet orbits. That does not automatically mean there is a clock in the Milky Way controlling events on Earth's surface. One statement is grounded in celestial mechanics. The other requires evidence that has not been demonstrated. This is a useful reminder of how easily motion can invite a story larger than the measurements themselves. The solar system really is traveling through a changing galactic environment. But the meaning of that journey has to be inferred carefully. For our own path, something simpler is already enough. Imagine Earth moving around the Sun. The Sun travels around the Milky Way. Now add the Sun's slow motion above and below the galactic plane. Add the small motion around the solar system barycentre and allow Earth's own orbit and axis to change gradually across thousands of years. There is no single clean spiral left. But neither is there chaos. Each motion follows gravity on its own scale. The yearly orbit belongs naturally to the Sun. The solar system's larger orbit belongs to the galaxy. The vertical oscillation comes from the galactic gravitational field, and the small shifts within the planetary system come from bodies pulling on one another. They can all be present at once because they describe different layers of the same system. By this point, the original question has begun to change. We started by asking what Earth's real path through space looks like. But perhaps the word real is doing more work than it should. Relative to the Sun, one path is useful. Relative to the galactic center, another is useful. Neither has cancelled the other. We have simply changed the coordinates around Earth, and that change of coordinates is not only useful for drawing trajectories. In one especially quiet experiment, Earth's yearly motion becomes part of the measuring instrument itself. Deep beneath the surface, physicists have spent years watching for tiny signals that might rise and fall with the seasons. Not because the detector changes, but because Earth does. Most of the matter in the Milky Way does not appear to shine. Astronomers infer its presence from gravity, from the way stars move through galaxies, from the motions of galaxies inside clusters, and from the way large concentrations of mass bend the light passing around them. The name given to this unseen component is dark matter. We know what its gravity appears to do. We do not yet know what it is made of. One possibility is that dark matter consists of particles that interact only very weakly with ordinary matter. If such particles surround the Milky Way in a broad halo, then the solar system should be moving through that halo as it travels around the galaxy. And this is where Earth's yearly orbit becomes useful. Earth moves around the Sun at roughly 30 kilometers per second. That velocity continually changes direction. For part of the year, Earth's orbital motion has a larger general direction as the solar system's motion through a simple model of the galactic halo. About half a year later, that component points more nearly the opposite way. Under the standard halo model, this should create a small annual change in Earth's speed relative to the surrounding dark matter. The expected difference is not enormous, but particle detectors are built to look for effects that are not enormous. In the standard picture, a hypothetical interaction rate could rise slightly toward early June and fall again toward early December. The exact phase and size depend on the assumed distribution of dark matter in the galaxy, which is why this seasonal prediction should not be treated as universal for every possible dark matter model. The idea is sometimes described as a dark matter wind. That phrase is useful only as an analogy. Nothing is blowing through a laboratory in the ordinary sense. The image simply reflects relative motion. A car moving through falling rain meets more raindrops on its front windshield when its speed through the rain increases. In a similar way, if Earth moves through a population of dark matter particles, changing relative speed could change the rate at which hypothetical particles cross a detector. The challenge is that any such interaction would be extraordinarily difficult to identify. Cosmic rays arrive constantly from space. Radioactive materials in rocks and construction materials can create signals of their own. Even tiny traces of contamination matter when an experiment is searching for rare events. So dark matter detectors are often placed deep underground. Layers of rock above them produce much of the background produced by cosmic rays. Inside, carefully selected materials wait for events that ordinary physics cannot easily explain. One long-running experiment in Italy, Gamma Libra, uses sodium iodide crystals. For many years, the collaboration has reported a yearly modulation in its event rate. The timing resembles what might be expected from Earth's changing motion through a simple galactic dark matter halo. That result became especially interesting because the experiment was not merely looking for a single unexplained flash. It was looking for a rhythm, a signal that returned year after year. If Earth's orbital velocity really changes our motion through a dark matter population, then a yearly pattern could provide a distinctive clue. But a repeating pattern is not enough by itself. Other effects on Earth also change with the seasons. Temperature changes, atmospheric conditions change, background radiation can vary, detector behavior can drift, and most importantly, another experiment using similar material should be able to test whether the same pattern appears elsewhere. That is why experiments such as COSIN 100 and Anais 112 became so important. They also use sodium iodide crystals, allowing a more direct comparison with the Gamma result. Their measurements have not reproduced Dharma's claimed dark matter-like annual modulation. With its full multi-year dataset, COSIN 100 found results in significant tension with the interpretation that Gamma's modulation is caused by the standard dark matter signal being sought. Anais has likewise reported results inconsistent with that interpretation. So the present situation is subtle. Gamma continues to observe a seasonal modulation in its own detector, but independent experiments using similar target material have not confirmed that the modulation comes from dark matter. The cause of Gamma's pattern therefore remains unresolved. For our journey, however, the importance of these experiments does not depend on Gamma being right. The deeper point is that Earth's motion is measurable in consequences far smaller than anything we can feel. The same planet that seems to trace a simple ellipse in a school diagrams changes its velocity relative to the galaxy throughout the year, and physicists can use that changing velocity as part of an experimental test. Earth is not merely sitting beneath the apparatus. Earth is moving the apparatus through a larger reference frame. That idea carries us back to the question we began with. From the Sun, Earth's orbit is almost closed. From the galaxy, that orbit rides on top of a far greater motion. And for a detector searching for dark matter, even the direction Earth happens to be moving within its orbit may matter. There is still one larger frame we can choose, a frame that does not use the Sun, or the center of the Milky Way, or even the nearby flow of galaxies as its starting point. Across the sky, astronomers can measure a faint background of microwave radiation left from the early universe. It is almost the same temperature in every direction. Almost. And that small difference gives us one more way to ask how we are moving. The Milky Way is not traveling through an empty, featureless universe. Our galaxy belongs to the local group, a collection that includes Andromeda, the Triangulum Galaxy, and many smaller galaxies bound together by gravity. The local group itself is not perfectly at rest relative to the larger distribution of matter around it. Nearby galaxy clusters, more distant concentrations of galaxies, and vast underdense regions all contribute to a complicated pattern of motion. One famous name in this story is the Great Attractor. For many years, astronomers used that name for a region in the direction of the constellations, Norma and Centaurus, where the motions of nearby galaxies seem to point toward an unusually large concentration of mass. The phrase can make it sound as if there is a single enormous object pulling the Milky Way toward itself. The real picture is broader. The Great Attractor region is part of a much larger gravitational landscape. Galaxy clusters and superclusters contribute, so do still larger concentrations of matter, and even regions containing less matter than average can affect the pattern by allowing galaxies to move away from them more easily. Our motion through the nearby universe is, therefore, not a simple journey toward one destination. It is the combined result of an uneven cosmic landscape. This creates a familiar problem. If the Milky Way is moving relative to nearby galaxies, and those galaxies are moving relative to still larger structures, where should we place the final set of coordinates? There is no universal grid painted behind the universe. But cosmology gives us something unusually useful: the cosmic microwave background. This radiation reaches us from every direction in the sky. It comes from a time when the universe had expanded and cooled enough for electrons and atomic nuclei to combine into neutral atoms. Before that transition, free electrons scattered light repeatedly. After neutral atoms formed, photons could travel far more freely. Those ancient photons have been moving through the expanding universe ever since. As space expanded, their wavelengths stretched. Radiation that once belonged to a much hotter early universe now reaches us mainly at microwave wavelengths, corresponding to a temperature only a few degrees above absolute zero. Across the sky, that temperature is remarkably uniform, but not perfectly uniform. Tiny variations contain information about the early distribution of matter that later grew into galaxies and clusters, and across those smaller variations lies a much larger two-sided pattern. One side of the sky appears very slightly warmer. The opposite side appears very slightly cooler. This broad pattern is called the CMB dipole. Most of it can be understood as a consequence of our own motion. As the solar system moves relative to the frame, in which the microwave background is nearly isotropic, but radiation arriving from the direction of motion is shifted slightly toward higher energies. In the opposite direction, it is shifted slightly lower. The effect is tiny, but it can be measured. The ability to measure it developed over decades. The COBE satellite produced the first full sky maps that established the microwave background as a precision cosmological dataset. WMAP later mapped temperature variations with much finer detail. Planck improved the measurements again, producing high-precision maps across multiple microwave frequencies. These missions had to separate the ancient background from radiation emitted by our own galaxy and from other foreground sources. The resulting maps are therefore not simply photographs. They are measurements built from detectors, calibration, frequency comparisons, and careful modeling of what lies between us and the early universe. From the dipole, astronomers infer that the solar system barycentre moves at roughly 369 kilometers per second relative to this cosmological frame. That number may sound like the answer we were looking for. Perhaps after changing frames several times, we have finally found Earth's true speed through the universe. But we have not. The cosmic microwave background provides a particularly useful reference frame because it is tied to the large-scale expansion of the universe. It does not provide an absolute state of rest. Earth still moves around the Sun within this frame. The Sun still moves around the solar system barycentre. The solar system still moves through the Milky Way, and the Milky Way participates in larger motions of its own. If we wanted Earth's trajectory relative to the CMB, we would have to combine those motions with Earth's changing position throughout the year. The path would be more complicated than the textbook ellipse, but it would not be more true. That is the quiet answer hidden inside all of these moving frames. The familiar diagram of Earth around the Sun is not a simplified version of some single ultimate path waiting to be revealed. It is one correct description chosen for one purpose. A galactic map provides another. A dark matter experiment may care about another. And the microwave background gives cosmologists yet another useful way to describe our motion. The path changes, Because the question changes. And now, with the largest frame of our journey in place, we can return to the small ellipse where we began. We began with a simple picture, the sun near the center, Earth moving around it once each year, a thin line closing back on itself. Nothing about that picture has become false. We have only carried it into larger frames. From the sun, Earth follows the orbit we know. From the center of the Milky Way, that same yearly motion is carried along a much greater journey as the solar system circles the galaxy. The sun itself makes smaller motions around the solar system's shifting center of mass. Across longer spans of time, Earth's orbit and axis change gradually. And on galactic scales, the solar system moves above and below the broad plane of stars. Each layer adds something. None erases the one beneath it. If we choose the cosmic microwave background as our reference, we can describe another motion again, with the solar system traveling hundreds of kilometers each second relative to that ancient radiation. But even there, we have not discovered a final stationary platform outside the universe. We have simply chosen a frame that is especially useful for cosmology, so there is no single picture that must replace the familiar ellipse. There is no need for Earth to have one ultimate line through space. A trajectory answers a question. Where is Earth relative to the sun? Where is it relative to the galaxy? How is a detector moving through a model of the galactic halo? How does the solar system move relative to the microwave background? Change the question, and the path changes with it. Perhaps that is why the simplest solar system diagram remains so useful. It does not attempt to contain every motion at once. It removes what is unnecessary so that one relationship becomes clear. Earth goes around the sun. For calendars, seasons, planetary navigation, and much of astronomy, that is exactly the picture we need. And when we need a larger picture, we can choose a larger frame. The ellipse then begins to travel. The sun begins to move. The galaxy becomes part of the story. And what first seemed like one orbit becomes several motions quietly layered together. At this moment, Earth is moving around the sun. The sun is moving through the Milky Way. The Milky Way is moving within a much larger pattern of galaxies. None of those motions is something we feel beneath our feet. The ground remains steady. The sky turns at its familiar pace, and the small planet beneath us continues along paths that depend entirely on where we choose to stand and watch. So if you return to that first drawing now, with its sun and single oval line, you do not have to imagine that something important was missing. The drawing was answering one question. Tonight, we simply asked another.